Welcome to The Explainer. Today, we're diving into a high-level procurement insights briefing that is custom-built for industrial buyers. Look, if you're sourcing materials for steelmaking, water treatment, or heavy construction, you already know that the supply chain is completely unforgiving. So we're going to master the engineering logic behind lime grades. Our goal here is to help your procurement team prevent incredibly costly and honestly completely avoidable errors. We're going to unpack the science, the real-world applications, and the freight economics of quicklime versus hydrated lime. Let's get into it. Here's our roadmap for today. We're going to cover the core dilemma, chemistry and kinetics, hidden specs, application matchmaking, and wrap it all up with the commercial takeaway. Section 1. The core dilemma, treating all lime identically. Far too often, teams treat calcium oxide and calcium hydroxide like they're the exact same, completely interchangeable commodity. Why? Simply because they both have lime in the name. But this quote really hits the nail on the head. Purchasing teams that treat CaO and CaOH2 as one commodity called lime usually find the difference at the worst possible moment: a blocked injection lance, a slaker running away. I mean, when you're managing an electric arc furnace or a massive municipal water treatment plant, a blocked lance or a runaway thermal reaction, that's not just a minor hiccup. That is a full-stop production disaster. This is exactly what happens in the real world when you treat a complex chemical purchase like a generic bulk order. Section 2. Chemistry and kinetics. What the kiln and hydrator change. To buy this material correctly, we really have to look at the underlying science for a second. Both of these products actually start as the exact same rock, high calcium limestone. But just one pass through a kiln gives us quicklime, which is highly porous, super thirsty, and born at up to 1250 degrees Celsius. Now, on the flip side, if you react that quicklime with a very precise stoichiometric amount of water in a hydrator, you create hydrated lime. The result of that process is a dry, free-flowing powder that's already hydrated. That means it is thermally inert and it behaves as a suspension when you mix it with water. And that difference in thermal behavior, it is absolutely massive. When quicklime reacts with water, it releases roughly 1,140 kilojoules of heat per kilogram. It's a violent, boiling exotherm. That massive number proves exactly why you cannot, under any circumstances, put quicklime into a closed, heat-sensitive dosing line or a system without a dedicated slaker. If your process can't tolerate extreme heat, quicklime is 100% the wrong choice. But let's say you want to aggressively dry out a wet, high-plasticity clay subgrade on a construction site. Well, that massive heat release is exactly what you're paying for. Moving to Section 3, hidden specs. Why relying on CaO percentage alone is a mistake. All right, it's time to bust a major industry myth. So many buyers just slap CaO greater than 90% on a purchase order, send it off, and call it a day. But here's the thing. A chemically compliant lime can still be completely useless to your engineers if it was overburnt in the kiln. That is exactly why the T60 reactivity metric is so vital. It basically measures the time a standard slaking test takes to reach 60 degrees Celsius. See, a soft burnt lime keeps its microscopic pore structure so it reacts aggressively and fast, often in well under 5 minutes. But a hard burnt or overburnt lime, its pores have literally been melted and sintered shut in the kiln. So yeah, it might technically be 90% pure, but it's going to react incredibly sluggishly. For critical high-speed processes like electric arc furnace steelmaking, engineers have to specify this reactivity metric or they'll literally just be left sitting around waiting for their slag to form. When you're reviewing certificate of analysis standards, you'll notice something really interesting. Even the absolute highest purity hydrated lime tops out at around 72 to 73% available CaO. Why is that? Because pure calcium hydroxide is only 75.7% CaO by mass. The rest of it is just chemically bound water. And this is exactly why available lime, meaning the fraction of calcium that's actually able to react in your process, is the commercially meaningful number you need to be tracking, not just the total purity. Section 4. Application matchmaking. Matching the grade to the process. Let's connect these specific technical grades directly to some precise engineering requirements. In steel metallurgy, kinetics dictate absolutely everything. You need milled Super 90 quicklime because it dissolves early, which builds a foaming slag faster and shortens the furnace's power on time. If you're using pneumatic injection lances, you've got to have the fine mesh 170 quicklime. Now, for treating really wet soils, the coarse mesh 70 quicklime brings all that heat and drying power we talked about earlier. But if you're doing urban soil work where caustic dust drifting away is a major hazard, you've got to switch to the highly stable Mesh 250 hydrated lime. And when it comes to water treatment, one core rule governs everything: fineness. Calcium hydroxide has incredibly low retrograde solubility. That actually means it dissolves less as the water gets warmer, which is pretty wild. So dosing it into a system is essentially just dispersing a solid suspension. If you don't buy an ultrafine product like Mesh 400, those coarse particles are just going to settle in your pipework. They'll act exactly like liquid sandpaper, completely destroying your expensive diaphragm pumps and injection nozzles with all that grit. Finally, Section 5, the commercial takeaway: freight economics and safety realities. Pivoting over to macro-level logistics, there's a crucial point for long, expensive sea freight legs, and it comes down to this number: 32%. A ton of quicklime delivers roughly 32% more available alkalinity than a ton of hydrated lime. Remember, when you buy hydrated lime, nearly a quarter of its mass is chemically bound water. When you choose quicklime, you aren't paying international freight rates just to ship water across the ocean. You're getting pure, incredibly dense neutralizing capacity. And bulk density totally dictates your freight arithmetic. Hydrated lime powder sits down around 0.45 tons per cubic meter, while quicklime lump is way up there at 1.55. So think about it. When you're paying for space on a cargo ship, hydrated lime powder takes up nearly 3 times the volume of quicklime lump. On a long sea route, buying alkalinity rather than just sheer tonnage heavily favors quicklime. But, of course, here's the catch. Buying CaO, quicklime, means you own the sleeking step. All those massive freight savings we just talked about, they are entirely nullified if your destination site doesn't have a sleeker that's safely sized to handle that violent exotherm and the resulting grit. You also need really good process water. Sleeking with hard or sulfate-rich water right on site produces a visibly poorer hydrate. So if you don't have the heavy equipment to sleek it safely, you really have to buy hydrated lime, regardless of that freight premium. We also definitely need to correct a very dangerous safety error that's super common in the industry. People often assume that because hydrated lime is thermally inert, like it won't boil water, that it's completely safe. But it is not chemically inert. A saturated solution of calcium hydroxide sits at a pH of 12.4. That is highly caustic to your skin, your eyes, and your respiratory tract. Hydrated lime requires strict, rigorous PPE, exactly like quicklime does. The hazard simply changes from a thermal one to a chemical one, but make no mistake, the danger remains. So let's wrap up this explainer with a repeatable, practical framework you can actually use. Next time you issue a purchase order, I want you to ask these 4 questions. 1. Does your process want heat, or does heat hurt it? 2. Is there a slacker on site? 3. Does the powder pass through fine dosing nozzles that require a strict Mesh 400 grade? And 4. Is freight a major share of your landed cost? Answer these, and your procurement team will never block a lance, ruin a pump, or overpay for water weight again. So, looking at your current supply chain right now, are you truly buying the right lime or just the right name?